Okay, this is the homework video for Thursday's lesson. We're looking at some more examples from exercise 4F. I'm going to look at question 7. In class this morning we did questions 9A and 10A. So now I'm going to look at question 7. I'm also going to look at question 11 now, and maybe a couple of questions from over the page. Is question 7, and the question is, if alpha and beta are the roots of the equation 2x squared plus 5x minus 4 equals 0, find the following. So the first thing is alpha plus beta. Remember, alpha plus beta is just minus b on a, which is, there's your b and there's your a, which is negative 5 on 2. Part B of the question is to find alpha times beta. Remember, alpha times beta is C on A, so it's negative 4 on 2, which is negative 2. Now, you've done questions like A, B, C. It's actually question D down here that's a little bit different. Part C, find alpha squared plus beta squared. Now, alpha squared plus beta squared comes from alpha plus beta squared. But if you expand alpha plus beta squared, you get alpha squared plus 2 alpha beta plus beta squared. So therefore, this left-hand side here does not equal the right-hand side, because the expansion on the right-hand side gives me alpha squared plus 2 alpha beta plus beta squared. So I've got an extra plus 2 alpha beta here, so I have to take away the 2 alpha beta. Now I can just show that here over the side. If I do alpha plus beta squared, I get alpha squared plus 2 alpha beta plus beta squared. But the thing is, I don't want the 2 alpha beta. I just want the alpha squared plus beta squared. So just looking at that, the alpha squared plus beta squared bit, which is just those two bits, is actually the alpha plus beta squared if I take this 2 alpha beta over to the left. Okay, I get the alpha squared plus beta squared is alpha plus beta all squared minus 2 alpha beta. So therefore, alpha squared plus beta squared is alpha plus beta squared minus 2 alpha beta. Now we know what the answer to alpha plus beta. We know that answer. It's negative 5 on 2, and we square that. Minus 2 times alpha beta from part B is negative 2. So we've got 5 on 2 squared, which is 25 on 4. Minus 2 times negative 2 is plus 4. So we've got 6 1/4 plus 4, which is 10 1/4, which happens to be 41 on 4. So that's your answer for part C. Now, you've done those before, okay? Part D is what is a little bit different, okay? Now, alpha cubed plus beta cubed. Remember, this is part D is done after part C, so it's going to use the result from part C. So if we just play around a little bit with alpha cubed plus beta cubed, it would obviously, if we start with alpha squared plus beta squared, actually what I'm going to do is actually just going to rub that out. If I'm trying to get alpha cubed plus beta cubed, it would more than likely come from alpha squared plus beta squared, and if I multiply that again by alpha plus beta, let me see what that gives me. I know it's not going to give me exactly alpha cubed plus beta cubed, but I can rearrange it, okay? So if I've got alpha squared plus beta squared and times it by alpha beta, I get, now alpha squared times alpha is alpha cubed, alpha squared times beta is alpha squared beta, beta squared times alpha is beta squared alpha, and beta squared times beta is beta cubed. Now I just want alpha cubed plus beta cubed. So I'm going to put that all together. So I've got alpha cubed plus beta cubed plus I've got this alpha squared beta plus beta squared alpha. That's what all of this is equal to. So actually I'm going to put that over here. Alpha squared plus beta squared times alpha plus beta, get rid of that, is equal to this. I've expanded it. Then I've put these alpha cubed and beta cubed up the front there. Now what I'm going to do here, I've got alpha cubed plus beta cubed plus, I'm going to factorize these two terms here, and I get alpha and beta in common here, and I'm left with an alpha plus beta. So I've got that alpha squared plus beta squared times alpha plus beta is equal to this down here. Now in part D, I just want to work out what alpha cubed plus, sorry, that should be a cubed, what alpha cubed plus beta cubed is. So if I just want those two, I'm going to bring this down here too. So if I just want alpha cubed plus beta cubed, it's equal to all of this minus all of that. So I'm going to take everything over to the other side. So alpha cubed plus beta cubed, that is this alpha squared plus beta squared times alpha plus beta. So it's this minus that, so taking this over to the other side. Now, we have the answers to all of these from parts A, B, and C. So alpha squared plus beta squared is 41 on 4 from part C, times alpha plus beta is in part A, it's negative 5 on 2, minus alpha times beta is from part 2. Now it's minus alpha beta, so it's minus negative 2, and that's being multiplied by alpha plus beta, which again is negative 5 on 2. So we've got 41 on 4 times negative 5 on 2 is negative 205 over 8. Then we've got 2 times negative, well, we've got a negative, negative, and negative. So this is all going to be a negative when I multiply, like minus, these two become a positive, and a positive times a negative is a negative. And 2 times 5 on 2 is 5. So it's negative 205 over 8 minus 5. Now, the answer to that, I'll just work that out. So negative 205 on 8 is actually negative 25 and 5/8 minus 5. And the answer is negative 30 and 5/8. Okay, so that's that answer there to part D. Now, part E is something that we haven't seen before. Okay, so it's a harder application of 2 units. So the absolute value of alpha minus beta. Now, we don't have any rules for alpha minus beta. Okay, what we do have rules for is things like maybe alpha minus beta squared. So if we say, well, that's really alpha minus beta squared, the square root of that. If I do alpha minus beta squared and I square root it, and whenever you take the square root of a number, you always end up with a positive number. So that would be the same as the absolute value of alpha minus beta, because remember here that the squared and the square root will cancel. So if we can work out what alpha minus beta squared is, and then we'll square root the answer, then we'll get the absolute value of alpha minus beta. Okay, now what I'm going to do, I'm going to just play around a little bit here on the side and work out what alpha minus beta squared is. Okay, sorry, you can't see any of that, I've just realized. So I'll start again. I want to work out the absolute value of alpha minus beta. Now that will be positive. The thing is, we can't work out, we only know how to work out, say, alpha plus beta, not alpha minus beta. So we could actually work out what alpha minus beta squared is, because that's a perfect square, and then square root it, because remember the squared and the square root will cancel each other out. So what I'm going to do, I'm going to come up with an expression for alpha minus beta squared. So if that's a perfect square, and if we expand it, we get alpha squared minus 2 alpha beta plus beta squared. Now I'm going to group the alpha squared and beta squared together, because that was actually my answer from part C, minus 2 alpha beta. So if we go back and look up at part C here, we've got that alpha squared plus beta squared is 41 on 4. So we can put that answer there. So looking back down here, alpha squared plus beta squared is 41 on 4 minus 2 times. Now alpha beta from part B is negative 2. So we've got 41 on 4 minus 2 times negative 2. So that's 10 and a quarter plus 4, which is 14 and a quarter, which happens to be, as an improper fraction, 57 over 4. So therefore, alpha minus beta all squared is 57 on 4. So therefore, the square root of alpha minus beta all squared is the square root of 57 on 4, which is the square root of 57 over the square root of 4, which is the square root of 57 on 2. Okay? And that's part E. Exercise 4F from the worksheet, question 11. And it says the polynomial in x equals x cubed minus lx squared plus lx minus m has zeros, alpha, 1 on alpha, and beta. You have to show that alpha plus 1 on alpha plus beta equals L. Now, we know that alpha plus 1 on alpha plus beta is just the sum of roots, one at a time. So sum of roots one at a time is alpha plus 1 on alpha plus beta, which is negative b on a. That's our formula. Sum of roots one at a time is minus b on a, which is minus negative L over 1, which is L. And so therefore we've just proven this first result there, that alpha plus 1 on alpha plus beta is L. I'm just going to call that equation 1. Okay, then if we look down here, it appears that we're multiplying roots 2 at a time. So sum of roots 2 at a time is, now we've got to do all the combinations of the roots 2 at a time. It would be alpha times 1 on alpha, so it would be alpha times 1 on alpha, that's one combination, plus alpha times beta, plus, so we've done the first two, the first one and the last one, now we'll do the last two, plus 1 on alpha times beta. So sum of roots 1 at a time is minus b on a, sum of roots 2 at a time is c on a. Now, if we simplify that, alpha times 1 on alpha, the alphas cancel and you get 1 plus, sorry, that's meant to be a multiply symbol. Alpha times beta is alpha beta, plus 1 on alpha times beta is beta on alpha. Now, C on A, we've got A, B, C. C is L and A is 1. So therefore, 1 plus alpha times beta plus beta over alpha is L on 1, which happens to be L. I'm going to just call that equation 2. Okay? Then we have to show that beta equals M. So let's look at product of roots. So let's write product of roots equals, we know it's minus d on a. So the product of our roots is alpha times 1 on alpha times beta is minus d on a. Now so it's minus, now our d is negative m, so it's minus negative m over 1. If you multiply alpha times 1 on alpha, these cancel and you get 1. So we get that beta is minus negative m, which is m. And so that's the third result that we've proven. So we've done parts A, B, and C where you have to show those things. Actually, it's A part 1, sorry, A part 2, and A part 3. We've just done those. Now for part B, we have to prove or show that. So we have to show that m equals 1 or that m equals L minus 1. Now we've got 3 equations that we're going to play around with. Now I'm going to write them all here again. So our 3 equations are alpha plus 1 on alpha plus beta is L. That's equation 1. Equation 2 is that 1 plus alpha beta plus beta on alpha is L. That's equation 2. And our third equation is that beta equals M. That's equation 3. So we're going to use these equations, these 3 equations now in part B to show that M equals 1 or M equals L minus 1. So what we need to show in part B, we've got M's, 1's and L's. So we've got M's, 1's and L's. Notice we've got no beta and no alphas. And we have to start with these 3 equations to end up with that result. So basically we need to eliminate the betas and the alphas. Our first substitution, maybe the best thing here to do, would be to replace the beta here with an M, and also to replace these betas here with an M. So we're going to substitute beta equals M into equation 1 and equation 2 from up there. So we've got that alpha plus 1 on alpha plus M equals L, and we've also got that 1 plus alpha times M plus M on alpha is L. So I've just replaced both these betas here with M's. So I've got alpha plus 1 on alpha plus M is L. And I've got 1 plus alpha m plus m on alpha is L. Now, I'm going to call this equation 4 and this one equation 5. Now, I'm really trying to get rid of these alphas from both these equations. So the best thing to do is to try and make alpha the subject. But before I do that, I can see that m is a common factor here. So I'm going to pull out the m. So I've got 1 plus m bracket alpha plus 1 on alpha is L. Actually, I'm going to call that one equation 5. Now, what I can see here is that I've got alpha plus 1 on alpha. And in equation 4, I've also got alpha plus 1 on alpha. So I'm going to rearrange equation 4 and write that, well, alpha plus 1 on alpha is L minus M. And I'm going to call that equation 4a. Okay, so now I'm going to substitute alpha plus 1 on alpha, which is L minus M, into here. So I'm going to go sub equation 4a into equation 5. So I've got 1 plus m times L minus m is equal to L. Now I'm going to expand that. So I've got 1 plus ml minus m squared is equal to L. Now this looks like a quadratic because I've got an m squared term and I've got an m term. I'm going to take everything over to the right to make the quadratic a positive one. So I've got m squared, and taking these two over, minus ml. Then I've got plus L and minus 1 equals 0. Now this is a quadratic equation, and where I've got the m, you would normally think of that as being x squared minus xl plus L minus 1 equals 0. So if those m's were x's, I would use the quadratic formula to solve, okay? So, and that would be x equals negative b plus or minus the square root of b squared minus 4ac over 2a. But in my case, the m is where my x would normally be. Okay, so I've got m is negative b. Now negative b would be the coefficient of the x, which is, or the coefficient of the m in this case, which is minus L. So it's negative minus negative L plus or minus the square root of, actually before I start, for this equation here, I've got that a is 1, b is the coefficient of the m here, which is minus L, and c is the constant term with no m's in it, which is L minus 1. So we're going to use the quadratic formula. So we've got m equals negative b, so it's negative negative L, plus or minus the square root of b squared, so that's negative L squared, which happens to be L squared, minus 4 times 1 times c is L minus 1, over 2 times 1. So we've got negative negative L is positive L, plus or minus the square root of L squared, minus 4 bracket L minus 1 over 2. So it's L plus or minus the square root of L squared minus 4L plus 4 over 2, which is L plus or minus the square root of, now this is a perfect square, and it's L minus 2 squared over 2, because we get L squared minus 2 times L times 2, which is minus 4L plus 2 squared is 4. So now we know that a square root and a squared cancel, so we get L plus or minus L minus 2 over 2. Now I'm going to put that L minus 2 in brackets. So we've got two scenarios here. This is what m is equal to. So therefore, m is L plus L minus 2 over 2, or it's L minus, so it's minus bracket L minus 2. So it would be minus L plus 2 over 2. Sorry, I'm being covered. So we've got L plus L minus 2, or L minus bracket L minus 2. So it's L minus L plus 2 over 2. So L plus L minus 2 is negative 2 over 2. Sorry, no, it's 2L minus 2. Sorry, so it's 2L minus 2. And this one, L minus L is 0, and we've got 2 over 2. Now 2L, sorry, just running out of room here. 2L minus 2 over 2 means to divide each of those terms on the numerator by 2. 2L over 2 is L, minus 2 over 2 is 1, so that's one of your solutions. and 2 over 2 is also 1. And so therefore, just coming up here, I've got a bit of room, therefore we've got m is L minus 1 or m is 1 as required. This is exercise 4F question 16A. Now this is a harder question. It would be heading into a band E4 for this question, okay? So if one root of the equation x cubed minus bx squared plus cx minus d is equal to equals 0 is equal to the product of the other two roots, show the following: c plus d squared is equal to d bracket b plus 1 squared. Now this is quite not really what you'd call a straightforward question, but you've just got to tackle it a little bit at a time. Now we know that one root of the equation is equal to the product of the other two roots. So first you need to define what your roots are, and we're going to let our roots be or equal alpha, beta. So that's the first two roots. Remember, this is a cubic, so it's only going to have 3 roots. So one root is equal to the product of the other two. So if these are my first two roots, then my third one will be the product of these two, which is alpha times beta. So there we've defined our roots, and they're alpha, beta, and alpha times beta. So there are our roots, and we have to show this result that c plus d squared is equal to d bracket b plus 1 squared. Notice that these are, you know, the coefficients of x squared, x, and the constant term here. So we're really going to have to be looking at sums of roots, product of roots. So sum of roots 1 at a time will give us something to do with the b. Sum of roots 2 at a time will give us something to do with the c. And product of roots will incorporate the d into that equation. Okay, so let's start. Sum of roots 1 at a time would be alpha plus beta plus alpha beta. Remember that that is minus b on a. If we do the substituting here, it's minus, now our b is negative b. So it's minus negative b on 1, which is b. So we've got that alpha plus beta plus alpha beta is b. Now that's equation 1. Now you've got to be very, very careful here because it's minus b on a. I know you've got a b here, but you've got to be careful that it's minus and then look up at what b is, and it's negative b. So you've got to be really careful with that, that you get a positive b there. So that was sum of roots 1 at a time. Now we're looking at sum of roots 2 at a time. Now when you do that, just make sure you're getting all of your combinations of roots 2 at a time. So we've got our first two, so we've got alpha times beta, then the first times the last one would be alpha squared beta, and then we look at the product of the last two, which is alpha times beta squared. Remember, sum of roots 2 at a time is c on a. Now, if you look up and see what c on a is, it's c over 1, which happens to be c. So what I'm going to do with this here, we can combine some like terms. Well, actually, there aren't like terms, but we can factorize these last two. So that would be alpha times beta plus, if we look at these two, they've got an alpha and a beta in common. So I'm going to go keep this alpha beta separate, factorize these two terms here, and you'd get alpha beta bracket alpha plus beta, and that equals c. The reason we're doing that is that it needs to be in terms of other things that we can see in other parts of the question, and also whenever you're doing sum and product of roots, we're always looking for combinations of alpha plus beta or alpha times beta. Okay, and we can already see here that we can make some substitutions from equation 1 into equation 2, because we could substitute alpha plus beta by taking this over the other side here. Okay, so there are some things here that we can do. Looking at that, I've had another idea, so I'm going to cross that out. Looking at these 3 terms, if we've got 3 terms, it's actually best if we can factorize all 3 terms rather than doing it like that. Another thing that's in common is alpha beta is actually in common in all of them. So if we say alpha beta is a common factor of those 3 terms, then alpha beta times 1 gives me this first term, and here for the second term I'm missing an alpha, and the third term I'm missing a beta. So this, if I factorize this, I'll get alpha beta as a common term to all 3. 1 plus alpha plus beta in brackets is equal to c. I'm going to call that equation 2. Okay. Then if we look at sum of roots 3 at a time, or in this case it'll be product of roots. So remember our roots are alpha times alpha beta. So that's alpha times alpha beta. Remember that's minus d on a. So alpha times alpha beta is alpha squared beta squared, which is alpha times beta all squared. And that's equal to, now d is negative d, so just be very careful there over a. So it's minus negative d, which is d on a. So we've got that alpha times beta all squared is d on a. So now we've got three equations here that we can manipulate, okay? Okay, now if you look at equation 1, you've got an alpha times beta in there. If you look at equation 2, you've also got an alpha times beta there. Sorry, actually over here, it's minus d on 1, which gives us minus d. So that's actually just a d. So minus negative d on 1 because the a is 1 and we get d. So therefore alpha times beta all squared is d. Okay? Now, that means that we don't want to substitute for alpha times beta squared. We're just looking to substitute for alpha times beta. So if we just look over here, therefore alpha times beta would just be the square root of d. Okay? Now we can substitute that into equations 1 and 2. Now if we go back and look at what we're trying to do, you're trying to show that c plus d squared equals d bracket b plus 1 squared. Notice that there are no alphas or betas in that whole expression. So what we're really trying to do with our three equations is to eliminate all the alphas and betas. So we know that alpha times beta is the square root of d, and we're going to put that into both equation 1 and equation 2. So let's do that now. So equation 1 will become alpha plus, so I've got equation 1 up here, so I'm substituting alpha times beta is square root of d into that. So I've got alpha plus beta plus the square root of d equals b. Now what I'm going to do, it'd be good to just put alpha plus beta on its own, would be b minus the square root of d. I'm going to call that equation 4. We're also going to substitute alpha times beta is square root of d into equation 2, so into this one. So we've got that alpha times beta, which you remember is the square root of d, times 1 plus alpha plus beta is equal to c. Okay, so again, substituting alpha times beta is square root of d into equation 2, we got this square root of d bracket 1 plus alpha plus beta equals c. Now we can see from equation 4 that alpha plus beta is b minus square root of d. So I'm going to substitute that in. So we get 1 plus alpha plus beta is b minus square root of d, and that equals c. So notice we've just eliminated all of the alpha and betas. So I'm just going to, so what we've just done there is sub in equation 4, okay, into that. Now, let's expand our brackets. So, because we notice that the thing that we're trying to find doesn't have any square roots in it. So it would be good to expand these brackets. Okay, so we get square root of d times 1 is the square root of d, plus, this would be b root d, and then we get minus d is equal to c. Now, a good strategy here to use is to keep everything with square roots on one side and take anything else without square roots over to the other side. Okay? The other thing we can now do, because we've got two terms on each side, what we're going to do is square both sides. So, actually, I can take out square root of d as a common factor first. So square root of d, 1 plus b, is equal to c plus d. So now what I'm going to do is square both sides. Okay? And that, the reason we're doing that is to get rid of the square root sign here with the d. So if I square both sides, I get square root of d bracket 1 plus b, squaring that side, is equal to c plus d squared. Now we're almost where we want to be up here. Okay, we're just about there actually. So square root of d squared is d bracket b plus 1, I'm just swapping the order of that, squared, is equal to c plus d squared, and that is the result that we wanted to prove, so therefore that equals that as required. Okay. Exercise 4F, question 17. Again, this is another tricky question that's a little bit different to some of the things that we've been doing. So we've got this cubic polynomial because it has a power of 3, and it has zeros alpha, beta, and gamma, such that gamma equals alpha plus beta. So the way that this would be worded is that one of the roots is the sum of the other two roots. So we could say, consider a cubic polynomial where one of the roots is the sum of the other two roots. So you would let the roots be alpha, beta, and gamma, but gamma would be alpha plus beta, which is the sum of the other two roots. In part A, you have to show that alpha plus beta is minus b on 2a, and we'll look at that first. Okay, now these are roots being added one at a time. You've just got to be careful because you're probably thinking, where's the gamma? But remember that gamma is alpha plus beta. So these roots are individual. So try sum of roots one at a time. So we know that sum of roots one at a time. Okay, so I'll just write sum of roots is equal to alpha plus beta plus gamma, which is minus b on a. Now, if we look up here at our equation, b is b and a is a, so it will just remain the same. But we know that gamma is equal to alpha plus beta, so we're going to replace the gamma with alpha plus beta, so we get minus b on a. And we've got two lots of alpha and two lots of beta, so we've got 2 alpha plus 2 beta is minus b on a, and we can see that 2 is a common factor, so 2 bracket alpha plus beta is minus b on a, and now dividing by 2, we get that alpha plus beta is minus b over 2a as required. So that's part A. Part B, we seem to have product of roots. Now you only seem to have 2 roots, but just do product of roots 3 at a time, because 2 of the roots are alpha and beta, and the other 2 roots are, and the other root is alpha plus beta. So I would still try product of roots and just see where that takes you. Okay, so the product of roots is alpha times beta times gamma, which is d on a. Okay, now we know but that gamma is alpha plus beta, so we'll substitute that in. Sorry, product of roots is minus d on a, and substituting that, we've got minus d over a. So we've got alpha beta times alpha plus beta, substituting the gamma for alpha plus beta is minus d on a. Now, from part A, we know that alpha plus beta is minus b on a. So I'm going to sub alpha plus beta is minus b over 2a into my equation above. It's equation 1, and I call that equation 2. I'm going to sub alpha plus beta is minus b on 2a into equation 2, and I'll get alpha times beta times minus b over 2a. So I'm putting this alpha plus beta in there is minus d over a. Okay, now I'm trying to come up with an expression for alpha times beta, so let's just put all of this other stuff over the other side. So I've got minus d on a, and if I put that 2a up there, I get times 2a over negative b, because I'm really like cross multiplying here. Okay, so I get alpha times beta is minus, the a's can cancel, and I get minus 2d over, over negative b, which happens to be 2d over b as required. So therefore alpha times beta is 2d over b. C of the question says, hence show that alpha and beta are also the roots of this equation here, 2abx squared plus b squared x plus 4ad. Now in that equation there, it's a quadratic equation, and in that equation, if I say sum of roots, I'm just going to go sum of roots. We know that the sum of roots is minus b on a. Now looking at what minus b on a is in this equation, we've got that a is 2ab, b is b squared, and c is 4ad. Just have to be really careful here. So minus b on a happens to be minus b squared over 2ab. So therefore the sum of roots, if we simplify that, we get minus, one of the b's there cancels with one of those, we get minus b on 2a. Now if we look back in part A, we know that minus b on 2a happens to be alpha plus beta. So therefore, the sum of the roots for this equation here is alpha plus beta, which is minus b on 2a. We can also look at the product of roots, okay? So we know product of roots is always c on a. And if we look at what c on a is in this equation, we get 4ad over 2ab. And that the a's will cancel and we get 2d over b. And if we look at part B of this question, we know that 2d over b is actually equal to the product of roots alpha and beta. So if alpha plus beta is minus b on 2a and alpha times beta is 2d on b, then we know that therefore the roots of this equation here are alpha and beta. So the roots of our equation, the roots of this equation are alpha and beta. Okay, that's the end of this question. You could please attempt exercise 4F from this worksheet, question 9b, 10b, question 12. Now question 15 is similar to what question 13 is in the worksheet. Now question 13 is very similar to what you saw in your textbook. So try question 15, but you'll have to define your roots. And questions 16, B and C, now they're fairly tricky as well. Okay, thank you.